Hello. Let's talk about different types of mixtures. There are three main types of mixtures we want to talk about: solutions, colloids, and suspensions. We're not going to talk a great deal about solutions. More of this is going to be about colloids and suspensions, but let's start off by defining them. A solution is another name for a homogeneous mixture. To recall, homogeneous mixtures are mixtures that are well mixed. They have the same composition and concentration throughout. Heterogeneous mixtures, on the other hand, are not fully mixed. Maybe there's a difference in sizes. You might be able to see different parts, but not necessarily. A colloid is one basically where the mixture remains mixed. The particles are small enough so that they don't fall apart. Whereas a suspension, the particles are so large they cannot remain mixed together without stirring or shaking or other agitation, and they will eventually settle. What type of mixture it is depends on the particle size. So something that is a very small difference between particles, where you have the same amount of size between one thing and the other, is going to be probably a true solution. Where you have a very large difference in sizes, very large particles here, that will be a suspension. And then a colloid would kind of go in between. If you recall some examples of solutions, again, a homogeneous mixture, well mixed, are things like salt water, lemonade, rubbing alcohol, gasoline, air, and steel. None of these are a single compound. They don't have a single formula. You can have different mixtures of gasoline. That makes it a mixture, but when you look at a gasoline from a gas pump, you should get the same amount of fuel, same quality of fuel with the first gallon as you do the last gallon. Drink lemonade, it should smell the same, taste the same, look the same all the way throughout. It is homogeneous. But what about a colloid? Well, a colloid from a distance may look like a solution, may look the same, may taste the same, may feel the same. But if you were to look up really close, maybe through a microscope, you might see there's a slight difference. For instance, a good example of colloid is milk. This is a picture of milk underneath a microscope. Now you might notice that there are these little bubbles inside this picture. That's the milk fat. If you think about milk, you might have something that's 2% or 1% milk fat. But most of milk is water, and we know that oil and water don't mix. So somehow these particles are small enough to remain mixed without separating, because when we get milk from the grocery store, it doesn't separate. It stays mixed. It stays looking the same throughout. So something must be going on here. There are lots of examples of colloids you might have in your home kitchen. Things, again, like milk, but also peanut butter, mayonnaise, jelly, whipped cream, and like Jell-O. These are all colloids. They look the same, they taste the same, they smell the same throughout, but they are heterogeneous mixtures. If you were to look at the different mixtures here up close underneath the microscope, you might find things like in mayonnaise, peanut butter, and whipped cream, fat. With jelly, maybe there's little pieces of, say, if you're talking about strawberry jelly, little pieces of strawberries in there. It doesn't settle out. It stays mixed in, but you can see the little parts there. With milk still, if you actually look at the side of a milk carton, I suggest you do this the next time you do have milk, it will probably say two words. You might be familiar with the first one, pasteurized. Pasteurization is the process by which milk is heated up, and that kills the bacteria in it. The more it's heated up and the longer it's heated up, the longer the milk will remain viable before you have to put it in a fridge. They actually do sell milk in Europe that's been pretty well pasteurized that can actually stay on a shelf. It's not in the fridge. You can go buy it on the shelf before you open it up. Once you open it up, you do have to put it in the fridge. But to do that, you have to heat up for a while, which actually causes the milk to get a brown color and change flavor a little bit. So Americans haven't gotten there. Our milk is still not fully pasteurized. We still like certain color, certain flavor. But the other word you might see on milk cartons is homogenized. Remember, colloid is a heterogeneous mixture, not a homogeneous mixture. So if you're talking about something being homogenized, you're trying to make it look more like a homogeneous mixture. When raw milk comes out of the cow, it separates into a fat layer. Basically, the fat is less dense than the water. It'll rise to the top, or you can skim off part of it. That's where our name skim milk comes from. The fat bubbles up top, the fat layer up top can be skimmed off. You can do that with a simple thing like a ruler if you really wanted to. But if you want to get it mixed in, you need to get the particles, the bubbles of fat smaller. So what you do is you basically take a big hose of it, shoot it at very high speeds through a grate that'll break up the fat bubbles, and it will cause it to be more like a homogeneous mixture. So it's been homogenized to make it approximate a homogeneous mixture, but it's still heterogeneous. The reason why this is happening, why these particles don't separate, why they stay mixed, is because of something called Brownian motion. This is where the particles are moving around, and basically they hit the big particle and keep it from falling out. So over here, I have a large particle just basically moving throughout this thing here, and all the other particles, let's say this is the fat bubble and these are all the water particles, are moving around. As you might remember from the kinetic molecular theory, all particles are in constant motion. So as the water molecules move around here, they basically just bump into this fat bubble. The fat bubble is bigger, it's more dense, maybe it wants to go downwards, maybe it wants to go upwards. It wants to leave basically the middle here, but as these things run around and bump into it, it keeps it moving through the water without letting it escape. So essentially the particle is too small to be fully mixed in. Too big to be fully mixed in, but too small to escape, and therefore remains kind of trapped in here. This can be seen in a lot of different ways. One of the things you're probably familiar with is the idea of saying like dust particles in air. I'm not sure if you could see this in the video, but if you have dust particles flying through the air currents will keep things up in the air, keep it mixed up until either there's not enough air currents or the particles might be too heavy and they'll settle eventually. But until they do, that's basically a colloid. Another common example would be fog. With fog, the mixture is large bubbles of basically water, and if you are capable, you might be able to look very close at fog and kind of even potentially see the water droplets dancing around. But they are essentially water droplets suspended in air. They're kept up and they won't settle to the ground. As a result of this, as a result that the particles stay in motion, stay mixed in, what happens is that the colloids tend to give us a kind of a cloudy look. This is something called the Tyndall effect. When you shine a light through a colloid, the light scatters and looks cloudy. So the pictures I have down here, we have a laser being shot through two glasses. In the first glass here, we have a solution. You can't see the laser beam in it. Over here, we have a colloid, and you might be able to make out that there's a red beam going through it. We can see the laser because as the laser runs through here, it hits a colloid, it gets dispersed, the light is scattered, and we can see it. Over here, it's just from the side, again, going through the solution. We don't see the beam. Hits the colloid, we can now see the laser beam. The Tyndall effect tells us that when light is shown through a colloid, it gets scattered. Now, I'm not sure if you can see that picture there. This might be a little easier for you. Again, we have a picture of a solution here. The light from a flashlight is shown through it. We don't really see the beam here, but when it hits a colloid, the colloid's beam, you can see that there is a little bit of cloudiness in the middle. We can see the beam being scattered, so we know that this one's a colloid and this one's likely a solution. Colloids scatter light. There are many different types of colloids. I've only shown you a few here with the idea of, say, liquids, but other words for colloids could be things like foams or emulsions, gels, aerosols. Colloids are very common in life. The third type of mixture was a suspension. Again, with the suspension, it is heterogeneous, but the particles are very large. So without constant agitation, being stirring, shaking, the suspension will eventually settle. So the particles here, let's say we're talking about a glass here of muddy water. If you have a glass of muddy water, these muddy particles, clay particles, will eventually be too big. The water will try to keep it suspended, but after a while, it'll settle. The big particles will settle out, and you'll get a lot more clear here. So with the large particles in suspension, they settle because they don't stay buoyed up by all the motion of the water particles. These could be things like muddy water again, or milk of magnesia. Milk of magnesia is a common medicine for treating heartburn, or orange juice with pulp, or Italian salad dressing. Basically, think of it this way. If you have to shake it or stir it before you eat it or use it, it's probably suspension. So the key difference between them is that solution is homogeneous. A colloid and suspensions are both heterogeneous. But the big thing that separates them is that suspensions will settle and colloids do scatter light. The suspension might scatter light. It might be cloudy, but it might not. But suspensions will always settle and colloids will always scatter light. So if you want to tell what it is, you answer the questions here in this order. You first ask, does the mixture settle? If you let it sit there without stirring it, without shaking it, will it settle? If the answer is yes, your suspension, you're done. If the answer is no, then you ask, does it look cloudy or will it scatter light if you shine a light through it? If the answer is yes, it's a colloid. If the answer is no, if it doesn't do either scatter light or settle, then it's probably a solution. So here's what I'd like you to do. I'd like you to try to figure out what these are. The answers are either a solution, colloid, or suspension. What are they? Storm clouds, white clouds, and a clear blue sky. Solution, colloid, suspension. Pause the video, think of your answer. Storm clouds are suspension. If you think about it, with the storm cloud, we have rain particles that are held up there by winds, but eventually the rain particles get so heavy, or ice or snow, they'll eventually fall out, they'll precipitate out of the air, and they'll settle down towards the ground. The particles become too big, they settle, suspension. White clouds, well, the clouds look cloudy. There's nothing falling out of them, so they stay mixed, but when the light is shown through a cloud, it'll scatter the light, it'll look cloudy, that's a colloid. If we don't see clouds, that means the light is coming from us directly from the sun. So nothing's settling out, nothing's falling out of the sky, and nothing looks cloudy. That's a solution.